Okay, here we go back again, and we're going to start off and develop the expression that we'll be using in the actual computer code in order to find the best fit. So we're going to start off with the gradient descent algorithm, and that one was theta sub j gets theta sub j minus alpha times the partial of j with respect to theta 1. So in order to implement this, we need an expression for the partial derivative of the cost function with respect to theta 1. So we'll start off, we'll rewrite the cost function. We have j of theta 1 is equal to, we're going to have 1 over 2m times the summation I from 1 to m, and then we're going to have inside of here, we're going to have theta 1 xi, that's our expression for our hypothesis function, minus yi, and then quantity squared. Okay? So we're going to start off taking the derivative of this expression right here. And first off, I'm going to set it up like this. Partial of j with respect to theta 1. I'm really doing the partial with respect to theta 1 of the whole thing, but the 1 over 2m and the I equals 1 to m portion, those are not affected by the derivative since they do not contain any of the theta 1 variables. So we treat every other variable when we're doing the partial derivative as a constant. So what we're going to do is take these two out of the derivative. So that will equal 1 over 2m summation I from 1 to m. And now we're going to have the partial with respect to theta 1 of theta 1 xi minus yi quantity squared. Okay? Now this hopefully rings a bell where we're doing when we're taking the derivative of a quantity that is squared, we're going to invoke the power rule. And since it's not just plain theta 1, we're also going to have to invoke the chain rule in return. So I'm going to start over with a new screen and start from that point. So the partial with respect to theta 1 of, we have theta 1 xi minus yi, and then that quantity squared. Well, that's going to equal 2 times the expression theta 1, oops, that's not an x there, I'll just change that like that, xi minus yi, and that will be to the first power. That satisfies the power rule, but now we invoke the chain rule, and we have to take the derivative of the interior of this. So the derivative of the interior with respect to theta 1 is just times xi. And that's it. So now my full expression is going to be theta sub j, it's theta sub j minus alpha times the partial of the cost function, which is 1 over 2m summation I from 1 to m of 2 times theta 1 xi minus yi, and then times xi. And that is our expression, almost, because we're going to do one simplification. The reason we put that 2 underneath is because it will cancel with this 2. So I can now cancel those 2, and we will have our final expression. The gradient descent is going to be our new theta, is going to be our old theta, minus alpha times 1 over m summation I from 1 to m of theta 1 xi minus yi times xi, and we are done. This is our new algorithm for gradient descent. And so when we are inputting it into the computer code, it is going to look identical to this expression right here. It's just it will be with lots of nice variables and everything else. So that will be the next step, is to actually start implementing the code. I'm going to type it in from scratch, every single one of the lines, and explain what they're all doing as we go. So hopefully it will make a lot of sense. All right, see you in a second. Okay, we are now inside of the Spider environment so that we can code up our one parameter linear regression. So let's start off. We'll start off putting in the chords. So I'll just come over here and say chords gets, and I'll do the same examples that we had before, where our points are just 1, 1, 2, 2, and 3, 3. And Python is very nice in that it lets you set up this two-dimensional array, if you will, or an array of points very, very easily. And so what I can do is come down here and say for point in chords. And what this will do is it will look at the chords variable, and it will pull out point by point as it loops through this for loop that we're going to establish. So one of the beautiful things about Python is the way that it handles for loops, is that you can use for and then define a new variable, which I'll call point, in that array, and it will pull out one array element at a time as it loops through the for loop without you having to do anything with indices or anything else. So very, very nice. Now, one of the stranger things about Python, if you're used to other languages, is that Python doesn't use curly braces for anything. The way you indicate a block of code is that you preface it with a colon, and then you actually indent, you space over for the entire time that you're in the block, and then when you stop spacing over, you are telling the Python language interpreter that you are no longer in that block. So for this one, what we'll do is we're going to make it read like English, or read like our algorithm, I should say. We're going to give the variable x point 0, so the first element of each of the points, so it's the x coordinate, and then we're going to give y the second element for point 1. Alrighty. And now we're going to sum up over all the points. So we're going to say sigma get sigma plus, here we go, we're going to have theta 1 times x, and then we're going to have minus y. This is our theta 1 times xi minus yi, and then the very last piece that we need for that is times x. And what this will do is that it will loop through every single one of the points and perform that summation that we need inside of our gradient descent algorithm. Now, before I can do that, I need to initialize sigma so that it starts with a value that will make sense. It won't just be holding a garbage value before we start. So I'll go ahead and initialize sigma as 0. And theta 1, I will also initialize, that's my initial guess, and I'll start off with a guess of 0 like we did with the example. So theta 1 is 0.0. Okay, now I've looped through that sigma operation. Now I'm going to build the full expression, and that one is, if you recall, I had the theta, the new theta gets theta 1 minus alpha, which we'll have to define that, times 1 divided by m times sigma. Okay, so what this is going to do is it's going to take the old theta 1 guess minus alpha, which we have to define, times 1 over m, which we also have to define, times sigma. So let's take care of the alpha and the sigma real quick. We'll let alpha be 0.1 to start, and we're going to say m is equal to the number of elements inside the chords array. That's the length of the chords array up here. So in that case, m will have a value of 3 since there are 3 set of points, 3 points rather, inside of the array. And in Python they say list, but I will be honest, I come from the old school arrays, and so I will probably say array rather than say list like I probably should when I'm talking about Python. So what do we have so far? We have initialized, we have a value for m, we have a value for alpha, we have an initial guess, we have our chords. We start off with sigma as 0, and now we are going to loop through each one of the points one at a time. They're going to be given to the x and y, and then sigma is going to be getting the sigma plus theta 1 times x minus y times x. So this will give me the sum of all points going through one at a time. Each one, the x is multiplied by the theta, and then subtract the y, and then that value multiplied by x again. So we have all of those things going on. That will give me my summation. So now I'll go through, this is the actual gradient descent algorithm. The new theta is the old theta minus alpha times 1 divided by m times sigma. Okay? Now, this would not be all that useful because this would loop through one time and then it would stop. So what we want to do now is we want to keep trying new theta values until we reach one that is at the minimum. And if you remember from where we were talking about the graphical representation, we were near the minimum when we had when we were at the bottom of the parabola. And at the bottom of the parabola, the slope was near 0, which meant that our new theta was very close in value to the old theta. So what I'm going to do now is take all of this and tab it over, because I'm going to put it inside of a loop. I'm going to say while diff is greater than some tolerance we're going to set. Tolerance, maybe that's how you spell it. I am definitely a terrible speller. So let me initialize both of these. Diff 0.0, tolerance, diff has to start off at something more than the tolerance. We'll just give that a value of 1 to start. 1.0 to make sure it's a float, and then tolerance gets, we'll say that we're going to stop our algorithm when we have the new theta is within 1/10,000th of the old theta. At that point, we're probably close enough to the bottom to where we can actually hazard a guess what the actual slope is. So while the difference is greater than the tolerance, I'm now going to loop through all of this, but now I need to update diff. So diff is going to get the absolute value of the new theta minus the old, theta 1, not old theta, just theta 1. And once I get that difference, I can say theta 1 gets new theta. So what this is doing is it is now assigning that value, the new theta value that we got, to the actual variable, so that when it loops back through, it will then use that value right there. If we didn't assign the new theta value to the theta 1 after we find the difference, it wouldn't update the theta values and we would just loop for forever. So that's how we're going to get around that. And I have to do one more thing. I have my sigma value that needs to initialize every time it starts into this for loop. It needs to be 0. Otherwise, it's just going to accumulate value every single loop through, and it eventually will hit infinity. So what I need to do, actually I don't know if it hit infinity, but it definitely won't work. So I'm going to reset my sigma to 0.0. So let's see if this makes sense. I am going, while the difference between my new theta and my theta 1 value, the guess and the new guess, the old guess and the new guess, I guess you could say, is greater than tolerance, I'm going to sum up all of the values in that sigma expression from my gradient descent, and then after that I will do the theta minus the alpha times the 1 over m times that sigma. That's the second part of the gradient descent algorithm, and then I'm going to then update theta 1, reset sigma to 0, and I believe that is about all I'm going to need. I hope this will work. So let's see if this works. I'm going to stop for a second and then I will resize my screen so you'll be able to see some different things. Okay, and we are back, and the only thing that I've changed is I've added a line that will print out the slope once we actually find it. Once it reaches the point where the difference between the new theta and the old theta is less than or equal to the tolerance, which we set at 1/10,000th. At that point, it will output the slope of the line that best fits is theta 1. And hopefully this will work. So let's run it and see what we get. And there we go. We knew that the slope of the line that best fit the data is, or should be, 1 and 0.9999 is within 1/10,000th of 1. So that is the value that we get. Of course, we know that it's actually 1. So the code actually works. The only thing I would change at this point is I would add something that would tell me how many iterations it had to loop through in order to find our code. So I'm going to add, let's see, I'll call it count, it's 0, and max iterations, it's maybe 50,000. So while diff is greater than tolerance and count is less than max iterations, and so I need to see right there. I need to add count, gets count plus 1. So what this is going to do is it's going to start out with a count of 0. It's going to loop through. It'll give a count of 1 at the very end of the loop. It'll come back up and see if that is less than max iterations. And if it is equal to the max iterations, once it hits 50,000, it will kick out of the loop. So that'll keep us from doing an infinite loop. And I'll actually add a little line here, print the number of iterations needed was, and then count. And now when I run it, there we go. We get that the count, the number of times it had to run until it found the slope, was 15. So now we can actually play around with it a little bit. We can change our alpha from 0.1 to maybe 0.2 and then run that. So now it found it in 5 iterations, so it is faster. We bump that up to 0.4. Yeah, once we bump it up to 0.4, you can see that, we jump up to 70 iterations. So alpha is very important in telling how long it's going to take to actually converge to the correct value. And if I enter too large of an alpha, maybe an alpha of, I don't know, 1, what we wind up seeing is the slope of the line that fits is a nan, which is not a number. So basically it diverged, it went to infinity, which is not a number, and it took 547 iterations to do so. On the other side, if I make my alpha really small, 0, 1, well, we start seeing some strange things. When your alpha's not too much larger than your tolerance, you're going to wind up stopping before you get down. So let me bump up the tolerance a little bit and then run it again. And there we go. And when I went from 0.1 to 0.001, I wound up increasing the number of iterations all the way up to 1800. That is impressive. So too small of an alpha, you're going to have many iterations needed to find your answer. Too large of an alpha, and it diverges. It goes to infinity, and you don't get an answer. So you always want to find the sweet spot for your learning rate, your step size for your alpha. A good rule of thumb is to start with 0.1 and try a few values out until you get the hang of what should be something that makes sense for your alpha. If you're dealing with large values, you might want to go to a 0.01 just to start with. But anyways, I digress. That is the code that will find the optimal slope for a set of values. In this case, we only had 3 data points using the one parameter linear regression with gradient descent and the derivative of the cost function. So I hope you enjoyed this, and I will be sending out this code with the very first homework where you'll get to play around with all of the values and see what you get.